Hello everyone, my name is Brendan from the University of Florida, and today I'll be presenting Lookout, a design framework for safety training systems, a case study on omnidirectional cinemagraphs. So the motivation behind our work is pretty clear. Safety is critical to worker health and productivity in any workplace. And we imagine VR and AR technology will be at the forefront of the future of work. So in this position paper, we discuss some key issues in designing training systems for different safety contexts and how to use an environment to enhance this training process. So given this, we present a general framework and define design variables for training environments. We also propose omnidirectional cinemagraphs, which can be used as a hybrid training environment that guides attention using motion while retaining spatial presence. And last, we evaluate this technology using a case study on kitchen safety training. So here we have our general design framework. Of course, there's a trainee, an intelligent system that measures their responses. So this could be interaction in the forms of pressing a button on a controller, or something that's behavioral, like heart rate or different eye movements. The intelligent system can then take this in and generate a response, such as moving to the next level or guiding the user to a hazard that they have missed. And the training environment is constantly updated to reflect this, and is of course perceived by the trainee through visual, audio, or haptics inputs to complete the loop between response and perception. Please see our paper for more details on some of the design variables for such an environment. And one issue we want to address is what distinguishes a safety training system from previous intelligent systems on tutoring. So these systems could be rule-based, give feedback. However, the hazard identification process is a little bit more complex than that. So we model this in 3 stages as see, recognize, and act. See refers to the perceptual process of noticing or attending to a potential area of interest, such as a spill, a poorly placed item, or an unusual reading on a meter. Recognize refers to the cognitive process of actually identifying that this is indeed a hazard. This leads us to act, which refers to making an appropriate intervention from the trainee. So the unique aspect of safety training is that we want to work on directing the user's attention to these potential hazards. What they do about it, whether they follow protocol, display some presence of mind, acknowledge it, is bottlenecked by the fact that they haven't seen the safety hazard. As a result, attention guidance is a key scaffolding in our training process. If we can guide trainees to the hazard regions, we may be able to improve their ability to see, recognize, and act within a training environment. So the new feature that we are proposing in the design framework is attention directability. It is the ability to afford several attention guidance techniques. So this includes visual guidance cues. We're used to these. These cues can be overt, such as a bright red arrow pointing to an object to guide attention, but they can also be subtle. So some of these techniques exploit the periphery to show a bright flash in the periphery that cannot be perceived, and they take it away before the eyes reach that point. Other cues can be diegetic, which means they're part of the environment or the scene that a trainee is within. So this could be something like a bright light source draws attention, while a non-diegetic cue, which isn't part of the environment, could be a bright green circle that's overlaid on the environment. These visual cues can also be static, so a bright red object will attract attention based on its color, or it can be dynamic. So when an object falls off a table in front of the user, they're going to follow that motion. And of course, there's auditory cues as well. So spatial audio is one example. A knock behind you could cause you to look behind you, but also directly, a narrator or instructor could tell you to look at this point or look in a particular direction. So all of the media that we explore in this work do indeed enable attention directability, but at different levels. And today we're going to focus on visual guidance. In particular, we propose omnidirectional cinemagraphs as they provide attention guidance through a well-established technique, motion, while still retaining presence and giving control over a photorealistic environment. So while 360-degree or omnidirectional videos and images also have photorealistic environments, they don't provide control over regions that move and remain static in a way that cinemagraphs do. So let me explain a little bit further. This is an example omnidirectional cinemagraph in the equirectangular format. So let me play it for you. So the first obvious motion that you can see is this large butterfly on the right-hand side of the frame. And what's happening is this motion is looped over time and continuous. So this could loop forever and will never stop. There's also some smaller butterflies to the top part of the frame and on the left-hand side. And it's important to note that there are some static regions as well, So we see people sitting on the back in a bench. So the actual input video, these people were having a conversation. However, with the cinemagraph, we don't want people looking at those folks on the bench. We want them looking towards the butterfly in this example that we're playing around with. So we animated the butterflies in other regions that are relevant and left the people static that are sitting on the bench. The idea is that we can control which objects, regions, and potentially hazards are static or dynamic interactively for any user. So using motion, we hypothesized that hazards would be more accurately identified by the trainee, and they're more likely to see them if they're animated than if they're part of static imagery. We evaluate our hypothesis using a case study on fire hazards and kitchen safety hazards. So an apartment scene was recorded using a 360-degree camera, the Verb 360, to get photorealistic environments. We staged 5 different hazards in this environment and created a cinemagraph using a tool called Cliplets from Microsoft, which is free to use. So for the study itself, 10 different participants took part in a between subjects experiment. And we measured safety in terms of how many hazards they could identify. So half of these participants saw the scene in a cinemagraph dynamic condition, while the other half saw them in an omnidirectional image or static scene. So at the end of the study, we presented 30 seconds worth of content and asked them to identify all the hazards within the scene. We also had them fill out several surveys, so scales referred to as attitude and preference, spatial presence, transportability, telepresence, and cognitive absorption were explored. With the data we collected, we used an Oculus DK2 to present the VR environment with integrated eye tracking. So we eye tracked all the participants and logged their data. So this is our recorded kitchen scene with all of the hazards labeled. Participants are told that they are viewing an apartment and that nobody is home. And they were asked generally to identify any hazards within the scene. So we have running water in the sink on the left-hand side. We have a burning candle that's placed next to some paper towels. We have a fan that's left on, is moving, blowing towards the candles and the paper towels. We have a burner that's left on for the stove and some boiling water in a pot on top of that burner. And last, we have a cloth that's placed over a burner right next to that boiling pot of water. So here's the cinemagraph version of that scene. You can see that the fan moves back and forth. It's very cyclic. It can repeat as many times as you want over time. The candle is also something that's cyclic, and the fire texture can be looped. The boiling water, the steam that comes out of it, can also be looped infinitely without looking jarred or looking like a standard linear animation. So our first takeaway was that the cinemagraph condition led participants to find more hazards in general than the static condition. And the next thing we explored was the scales that we measured. So we saw all of our scales actually had higher, more positive values in the cinemagraph condition. But 3 that we wanted to focus on where we saw bigger gains were the presence, cognitive absorption, and positive attitudes of the users. Using the eye tracking data, one metric that we explored was called time to first fixation, or how quickly did participants find each hazard. The result we found is that the motion of the fan that you saw in the middle actually guided participants to look towards their left from the starting point, which led them to the candle and the water faucet quicker than the static condition. And in the static condition, we found that viewers turned towards the right and identified those hazards with a lower time to first fixation. So an ongoing question with cinemagraphs is that motion may attract attention, but does it actually hold attention? And this should be evaluated with a slightly different gaze metric. So please read the paper for a little bit more analysis on the data we've collected for eye tracking, as well as discussion of our results. So to finish things up, we saw that the omnidirectional cinemagraphs have potential for safety training as they afford controlled visual attention guidance while retaining presence and cognitive absorption. However, these trends were just preliminary at the moment. And what we've seen, at least with this current study, is that we've animated hazards in parallel. However, in future studies, we can also animate hazards sequentially to see if the order that they're seeing matters to trainees. And there's, of course, some technical challenges as well. So how to generate omnidirectional cinemagraphs with the highest quality and to actually guide attention using the motion that we use. So in future work, we plan to explore trainees through different contexts, such as medical and construction, and see how the see, recognize, act paradigm works. So thank you for your time. Please read the paper and check out our website for more details. Thank you.